Welcome, everybody in the lecture hall. Welcome, everybody on Zoom. Welcome, everybody watching us from the future. So today we are going to be finishing the part about white column source and all the internal implementation. And then we will move on to data modeling, especially for trees. But before that, I have a question for you. So yesterday, the internet was partially down. A lot of services didn't work. And in fact, it had to do with Amazon, more precisely DynamoDB. And so my question to you is why, since I told you about systems that are available and eventually consistent, that's not supposed to happen. So why was the internet down? So is it because it was a DNS issue? And in fact, DynamoDB was perfectly available via IP addresses. Or is it because DynamoDB is not the same thing as Dynamo? That's the public service that was implemented later, while Dynamo was an internal project for shopping carts. And DynamoDB is actually CP, not AP. Or did you not notice that the internet was down? Raise your hands. Who didn't notice the internet was down? Some of you. Oh, wow, OK. Well, it was partially down. It was partially down. So we have a majority. And actually, the majority is correct. This is indeed the case. DynamoDB was still available. You could still connect to it if you knew the IP addresses, but the problem was a DNS issue. If you have a host name and you cannot resolve the IP address, then of course that has nothing to do with DynamoDB. The second answer is actually not entirely wrong because it is correct that DynamoDB technically is not the same thing as Dynamo. So DynamoDB is in fact a system that was a bit simplified to make it more usable by end users. And it has a few differences. And in particular, it's not entirely false that it's CP. More exactly, let's say the normal version of DynamoDB is technically CP. It's strongly consistent because it forces all the writes to go via a specific machine within an availability zone, which is a cluster of data centers. But the reads can be, the reads are still available because you can configure it to be able to read not necessarily the latest version. So you could say it's kind of AP for the reads or CP for the writes. Now, it has also a multi-region version where you can have a version of DynamoDB across regions, meaning US East, US West, Frankfurt, and so on. And then, indeed, it's also AP for writing because you can have different writes in multiple regions. But again, to clarify, what we covered is Dynamo, and that's not the same thing as DynamoDB. Is there a question? Small hops, small hops. Yes, go ahead. There you go.
Look at this, now I'm forgetting my own question. To my understanding, yesterday only US East 1 was down.
It was US East 1, yes.
Is it not the case that DynamoDB is split across multiple regions? And if so, why could the other regions not allow for recovery?
So indeed, you are correct that it was only US East 1. I think it was Virginia. There's a lot of data centers in Virginia. So that was US East 1. So the first thing to say is that you can configure the way you use DynamoDB. So maybe I can say a few words on the high level. And of course, the users can be using them in different ways. So I told you that you can pile up computers on a rack. You can put multiple racks in a rooms across multiple rooms, and that gives you a data center. And I stopped there. But in fact, you can also have multiple data centers, let's say 3 and 6, roughly in the same city, that you can connect together efficiently within milliseconds. That's called an availability zone. Exactly. So that's a small cluster of data centers. They still feel like it's a single local mega data center, right? And then you can have plenty of availability zone within a region. like US East, like EU West, and so on, Asia. I don't know the regions by heart anymore. So you have plenty of availability zones within a region, and then you have multiple regions in the world. So there's all these hierarchies of computers, just like the galaxies and the solar systems and so on in the universe. And now the idea is that within a region, if I'm correct, and if I correctly remember, you technically have CP rights in the sense that there's one leader for every partition of the data. But you can configure DynamoDB to be across regions. As you correctly said, you have the multi-region version of DynamoDB, and then you have it across regions. And then I assume that, of course, for the companies that did that, they might, I guess, they probably were in a better position, because if the DNS was only failing in the specific region, it should have worked otherwise. And I would assume that those who had a multi-region mechanism were not impacted, likely. Maybe this is why there was a lot of raised hands still in the room of people who didn't notice. But nevertheless, you can still use DynamoDB in a single region. So there's probably people who specifically had Virginia or specifically US East 1 as the region. And of course, since there the DNS was failing, then it didn't work, right? I was about to say within that region it's CP, but again, that's the DNS thing. It's not because it's CP on the rights within the region. It's really the DNS that caused the issue in that case, right? Did I actually answer your question, or I use it as an opportunity to define region, availability zones, data centers, and so on? I don't know, and why is Virginia so popular? You know, all these data centers. I think maybe it has to do with the number of companies or the intensity of the economy in the US. That might have to do with this. There's no reason why a company that is all over the world would specifically use US East, because normally you try to use the regions where the end users are. You want to avoid the latency, because across regions you can have tens or hundreds of milliseconds, and that's too much for a website. An international company is probably going to use multiple regions and replicate the data across regions. The smaller companies maybe cannot afford it, or maybe they are locally implemented somewhere, and then they would use the region that they have. Something else has to do with laws. That's another aspect of the availability zone and the regions. The regions, by the way, are completely isolated. You can connect the availability zone with each other, but the regions are isolated from each other. And that has to do with data protection laws, that kind of things that might force you to have your data specifically in some domain. For example, with GDPR in the European Union, you wouldn't be allowed to have your data in US East, for example. You would have to have them inside the European Union. That's an example. That's maybe not fully answering the question. I mean, it's known that US East is very popular, and there's a lot of data centers in Virginia. Maybe I can look at if there's any more reasons. Do you know, or is it another question?
Yeah, so I know a little bit. I read yesterday that US East was the very first CERN of AWS, and that some specific other services, I mean, not DynamoDB, but more specialized services only are available in US East. And so that might incentivize companies to just say, well, if we can use this particular bit only there, then we're just going to use all the services from that region.
That's a very good point. So there are services only in US East. Yeah, okay. I'll investigate that. Maybe there's interesting things to learn there. Yeah, thank you very much for your answer. Does this answer your question? All right. Any other questions or follow-ups, even on the material last week? Go ahead.
Just a random question. Generally, like I was reading that services like Snapchat and Reddit were down because of this outage. Doesn't like while we were seeing in like, I don't know which topic, but using in HDFS, generally the replicas are stored inside like different nodes. Doesn't that happen with regions as well? Suppose you are storing, and like in companies like Reddit and Snapchat, which are like huge firms, don't they like have their like servers and microservices located like in various regions? So if only a particular region was failing, how was it out? Like I wasn't able to understand this.
You're making a perfect transition to the end of today's lecture to the white column source. I will tell you what happens across regions. There are technologies that do that. Now, in terms of the mindset you should have with HDFS, typically when you have a cluster like that, think it's an availability zone, and I cannot even pronounce this. It's an availability zone or a single data center, right? You basically have all your nodes within the same HDFS cluster are in the same availability zone, right? So a few milliseconds of delay within this data center, right? Does it make sense? And I will tell you, I have plenty of slides that will show you how Google actually built a system that connects regions and that spreads the data all over the world. That exactly as you described, that you have systems that improve HDFS further and replicate all over the world. Maybe I can also say a few words on S3, like a service like S3 has to be associated with a region. So when you have S3 buckets, they are in the same region. And so the expectation here is that within an availability zone, there is a risk of fire or anything, local incidents. But typically within a region, it's large enough that it would be less likely that an entire region would fail in terms of losing data, right? Yesterday, there was no loss of already stored data, as far as I know, right? Does it make sense? Even though I didn't answer because I have the slides coming right up, right? But that's an excellent point, right? Yeah.
We have a question on Zoom.
Mm-hmm.
In HBase, how are columns split across families? We said that everything accessed together should be stored together, but how is this done exactly?
Let me see. I just didn't catch one word. So
Sorry, how are columns split across families?
that's what I know across?
In HBase, how are columns split across families? So I guess column qualifiers.
Or against in the families?
Yes, because they said we should access everything together, and it should be stored together. Everything accessed together should be stored together. But how is this done exactly?
Ah, okay, I see. Because the partition that we do in HBase is by region and by column family. And so we stored what is within a column family. But technically, the column families, the data from different column families in the same region would not be in the same H files and would not be in the same store, right? I would say that the answer to the question is that even though they are stored separately on disk, they are still the domain of responsibility of the same region server. So the region server that handles the region is going to be responsible for all the column families within that region. So this is, you could consider that there is proximity in this, that you have a single query that gets you all the column families within the region.
Okay, cool, thank you.
Okay, did that answer the question on Zoom? Maybe a quick
I
yes.
assume I'll follow up if not.
We can wait for a few seconds for confirmation. Yeah, all right.
Got it.
Awesome. Any more questions? Not in the lecture hall, not on Zoom? All right. Okay, so yes, that was a good opportunity to talk about, you know, it's the real life, all of this, what we are studying here. This is the real world that is using these things. Okay. So we stopped here, if I'm correct. I had this 2048 game where we have this, do you remember how we call when we have the memory is full, we? Flush, yes, I heard it. And when we have too many H files, we compact them. And when the H files become too big that even compacting them doesn't help, what do? We I mentioned it somewhere else in the lecture, but not in relationship with the H files. What do we do when the H file is too big? Or the region is too big? We split, exactly, we split. And that's exactly what happens. So we flush, we compact, and then we split, right? That would be the three in the order in which they happen. Okay, so now that's an idealized version. Of course, in reality, I told you there's minor compactions, major compactions that happen, but pretty much the sort of dynamic that you get is similar to this little animation. So now, I think there was a question that's kind of also the follow-up on some question that was asked about the fact that the mem store basically stores data that is not yet persisted to disk, right? So this is why we also need to query the mem store. So could we optimize things in the sense that we would still have in memory some of the data that is on disk, but if we have a copy in memory, it's faster to read? And the answer is yes, but it's not in the mem store because again, the mem store is for the fresh data. It's a cache, so we can have an additional cache that contains some of the data that is on disk that you can directly read from memory, right? It's a separate structure. Very similar to CPU caches, but of course on a much larger scale, right? For whom does that make sense? That we would do that, right? Okay, so we would have the cache. That's optimization number one. There's cases in which the cache is totally useless. An example in which the cache is totally useless is when you are really scanning through the entire table, the entire data set once. Then it doesn't make sense to keep it in cache because anyway, you're scanning the entire data set. So whatever you put in the cache, you will replace it by new data every time, right? So when you scan the entire table, when you have that kind of patterns, access patterns, the cache doesn't make sense. For whom does that make sense, that the cache doesn't make sense? Okay, awesome. There's another access pattern where the cache is not really useful is when you access the data a bit randomly, but there is no hotspot, right? A hotspot is basically when you keep writing or reading the data at the same point. We have a question over there. There you go, right, okay.
Does it cost us anything to use the cache? Is there any reason I mean, wouldn't this just occur based on access patterns? Or like, when we talk about like, you know, situations you would not want to use the cache, is there any cost to it or is it just hypothetical?
No, it's just saying that it would be useless. Basically, you would there be a cost? So basically, would it make it worse? Basically, there's a difference between it doesn't help and it makes it worse. That I don't know. Would it actually even cost something and make it worse than it already is? You would have to basically compare the access to the disk to accessing the cache. If it makes it worse, I don't think it would be much worse because the order of magnitude of accessing memory seems less than that of accessing the disk, but that would be a guesstimate, right? Could we make a note of that? Maybe I can also look it up offline, right? Okay, any other questions? All right. And of course, access patterns that make the cache useful is if you keep accessing the same zone or the same data. Then instead of repeatedly reading from disk, you can just fetch it from the cache, right? And of course, the mem store, right? Because the cache only caches the data that is on the disk. Okay. Then there is another optimization technique, which is you really have to keep this as a very generic idea of big data. When you need to read a lot of data from disk, which is expensive, accessing the disk is very expensive, accessing HDFS is expensive, you basically have processes or queries where the bottleneck is reading from disk. This is the disk I/O. Everything we look at, MapReduce, Spark, and so on, the bottleneck is the disk. It's reading the data from the disk. And so since this is your bottleneck, if you have a technique that tells you don't read from there and don't read from there because there's nothing to find here, then that's a huge help because you have to read less and then suddenly the time it takes diminishes. Who agrees with this idea, right? And that's a fundamental idea in big data, that we try to figure out what we don't need to read. And so one of the ways to do this in the case of DH files is to store at some place in the header of the DH files, intervals, for example. You could have intervals of values that correspond to certain columns, or intervals of column names, or intervals of row IDs. That tells you basically everything that is in this H file, is within that interval. Now, if the user requests data that is fully outside of that interval, then you can skip this H file when the interval doesn't overlap. Who agrees? Right? So this is a very important optimization technique. So basically, in that case, just as an example, I drew 17 H files, and 3 of them basically have an interval that does not overlap with the what the user is looking for, and so we can skip them completely. Right? So that's using intervals is the naive solution. And there's another thing that does that is the same idea, but instead of intervals, it's using hashes. Oh no, there it is, the hashes. It's just that it's almost the same. It's just that it's not intervals. It's a Bloom filter. A Bloom filter is basically using several hashes, and it's a system that can tell you for sure that some data is not in an H file, and that can tell you otherwise maybe it is in the H file. So it's not yes or no, it's no or maybe, right? And so it's made of different hashes that you take. When you create this Bloom filter, you take the hash of all the values you put in the H file, and you combine the hashes into a single hash table structure. And when you have to look up a value, you basically, again, take the hashes and see at the places corresponding to the hashes in the hash table structure whether there is at least one of them that might be occupied, whether all of them are occupied, and then that allows you to infer that the data is there or is not there. As an example, imagine that you use 3 hashes. So every time you put a value in an H file, you compute 3 hashes, and you put a marker for these 3 hash values in your hash table. And you do it for all the values. And then you have a query, and the incoming query has a specific value. You compute the 3 hashes, and you notice that out of these 3 hashes, maybe 1 is marked, and the other 2 are not marked. Who thinks we can conclude that for sure the data is not in there? Who thinks we can conclude that maybe it is in there? Okay, half-half. Let me ask another question. What if all 3 would be marked? You compute the 3 hashes, look them up in the hash table, and all 3 are marked. Who thinks that we know for sure it's not there? Who thinks we conclude that maybe it is there? Yeah, we have a majority, exactly. So in the first case, not all of them are marked. So in that case, you know for sure that it's not there. Because if it had been in there, all 3 places would have been marked, because we would already have seen the value before, right? So then it's a no. If all 3 are marked, then that's a maybe, because the hashes could come from other values that just collided, right? So that's why it's a maybe. For whom does that make sense, right? So the Bloom filter, that's the name for that, for this combination of hashes. This is similar technique to intervals, but even more efficient to tell you either no or maybe it's useful to read that H file. So this is a great technique. And we'll see it applies to so many places, this idea that whenever we can find a reason to skip files or to skip entire regions of the disk or HDFS blocks, then we save a lot of time in the query execution. Okay. Now, I told you a few words about a special table, that is the meta table, that contains information about all the regions. Who remembers this? The meta table? So the meta table looks like another one of the tables in HBase, but it's special. First, it's special because it's fully on one single machine. It's not spread across multiple machines. And second, it's maintained via a distributed system using, again, a quorum protocol, Zookeeper, to decide which machine, which one of the region servers is responsible for the meta table. And thanks to Zookeeper, everybody knows where that meta table is. So whenever somebody needs to fetch some data in some region, they just communicate with the meta table. They receive information on which region servers are responsible for the region in which the data is, and then they can connect to the region servers. So that is the meta table. And so the way it works is that, so of course, to create tables, delete tables, you connect with the HMaster. But if you want to fetch some data, you can ask for your region on the meta table. So you can assume that Zookeeper told you this is on this machine. Then you get back the region server locations. You might cache them if you want for efficiency. And then you query directly the region server for which that the meta table directed you to. Who is with me? Right, okay. In terms of API, it's still Java. So you can have a Java API if you want to program in Java. You have the REST API that gives you access, again, via HTTP, similar to how HDFS has one. And of course, you have access via the shell. You can also have a command line where you type, you can quickly run delete, get, put, scan queries in the command line. Right, okay. All right, and now I'm about to finish on HBase. I also wanted to follow up on a question regarding locality. That is something that was asked, I think, by multiple people about the fact that the region servers would read from the same machine. Because you remember that the region servers are co-located with the data nodes, right? It's processes on the same machines.
We have a question on Zoom. Sorry to interrupt. Why is the HBase :meta on one of the data nodes and not on the name node if it is centralized?
Oh, why don't we put it on the coordinator node on the HMaster?
Exactly.
It's actually a very good question. Why? In terms of design, I also would be tempted to put it on the region server because basically the rule is that the regions are handled by the region servers, right? And the HMaster only coordinates. So if you would also put it on the HMaster, you would end up with the coordinator node that also stores stuff or is responsible for storing stuff. And it kind of breaks the asymmetry between the worker nodes and the coordinator nodes. Okay. But it's a perfectly valid question to ask. You could also have said that the HMaster handles it. Then you would have to ask what happens in case of failure. If it fails, maybe it gives you more reliability or a better failover because you can easily handle the handouts, the responsibility of meta to another region server. Yeah, I'm just thinking out loud. That would be the thinking. So can you make a note?
Yeah.
I also look offline.
Sounds good.
Yeah, it's a perfectly valid question to ask. Did I successfully not yet answer your question so that I can come back to you? On Zoom? Oh, that was on Zoom. Yes. Yeah, I'm looking in the lecture, but of course it's not in the lecture. Yeah. All right. This is exactly the sort of design questions that the engineers who create these systems have to ask themselves, right? We have another question there.
Minor question, but is this meta table the same as the goods table? I remember like last week.
That's the same. It's the new name of the root table. I still sometimes say root table out of habit, but I'm supposed to say meta table now. Root table is a very old name from the first versions of HBase. It's the same. It's the same thing.
Thank you.
Yeah. Thank you. Oh. All right. So data locality. You remember that in the HDFS lecture, I told you that whenever a client of HDFS writes data blocks to a data node, the first chosen data node, the first replica is going to be stored on the same machine. Who remembers this? Right. Now, who is the client of HDFS now? Well, it's the region server, because the region server needs to write H files. So the region server connects to HDFS in order to create the files for the H files, technically. Because the region server runs on the same machine as the data node, then it is natural that one replica of every block of every H file that the region server creates will have a local copy on the same machine as the region server. Who understands this? Right, awesome. And then 2 more replicas on other region servers. Now, the consequence is that when you read the data, the same region server might need to read the data back. Do you see that it's a local read because we short circuit HDFS? Who sees that? Right, okay. So we can directly read. So this is here one node that runs a region server process and a data node process. And all the H files for the regions that the region server is responsible for have their first replica, one replica, stored locally. And so it's a local read, and we can bypass the name node, we can bypass HDFS and directly fetch them from here. But the problem is that, everything has a life, and then if you wait for a while, at some point, you might have some non-locality, some blocks might end up somewhere else. One ID might be because of some load balancing on HDFS. If you use the load balancing facility to redistribute the blocks, they might no longer be there. And then, of course, we split regions. So whenever you split a region, it doesn't move the replicas when you split a region, right? All you do is you first reassign the responsibility. But the thing is, when you split, at some point, you will have to split the H files. What does it mean to split the H files? It means you rewrite them completely in one half as new H files. And what happens is that it brings it back all to place the moment you do that. So every time you flush, every time you compact, every time you split, this is re-bringing locality to the system, right? So it naturally brings back the replicas of the block on the same machine because of the constant compaction and splitting that happens. For whom is that clear? For whom is that not clear? For whom is that clear? Okay, more resonance. Okay, awesome. So there is this idea of locality, right? If we have quantum physicists, it feels a bit like the wave function is just moving a bit apart, and then bam, we just collapse it back. Okay, so this is locality. It's very important because this idea that we are reading and writing the data to HDFS from the same machines on which the data nodes are allows us to short-circuit HDFS and directly read and write to and from the local disk. That's very important. We'll have that again in MapReduce when we use MapReduce. All right? So this is the idea of bringing the query to the data. Now to finish, I wanted to tell you that there's a whole ecosystem above HBase. You know that HBase, even though it's tables and relational tables, you remember everything is binary, it doesn't have any data types. It doesn't have any query language. There's just put, scan, delete, and get. But there is not SQL or anything like this on top of HBase. So basically what that tells us is that HBase is not a relational database management system because it doesn't have SQL, it doesn't have a query language. But fortunately, a lot of engineers have built things on top of HBase. So I can tell you a bit. So first, at Salesforce, they actually brought back a relational database management system in the sense of OLTP called Phoenix on top of HBase. It directly communicates with HBase. It's basically sort of translating SQL to queries that get, put, delete, and scan, right? So that would be Apache Phoenix. Then we have something more like the OLAP style that is called Apache Hive. And this one uses MapReduce. It doesn't directly communicate to HBase. It uses MapReduce, which we'll see in 2 weeks, in order to execute analytics. So full scans of the data, aggregation, and so on. Also with SQL, and then you can store it in HBase. Hive can also store it at plenty of other places. There's not only HBase, but that's one of the possibilities. So here we have Facebook, Netflix, Yahoo. Then we have Databricks, where we have Apache Spark that we'll see in probably 3 or 4 weeks that is able to connect with HBase, and Spark has Spark SQL. So you learn SQL, it will be useful. We'll see it back in Spark. Then we have alternatives to Spark, more in the sense of federating queries, meaning that they talk to plenty of different backends. So Presto would be the first one that was built, and Trino is kind of an expansion that came later that uses Presto. The idea of these, what I mean with federated, is that it doesn't just speak to HBase. It also speaks to plenty of other places and formats, right? That it queries. And then for the people who love to stream through data, so not just batch process, but also streaming, I'll tell you a few words in a couple of weeks too. There's Apache Flink that is able to use HBase as well. So you see, there's all these technologies that kind of bring back SQL into the picture as a way to interact with the system. Okay. Any questions? Yes?
On Zoom about regarding maintaining spatial locality. With compaction and flushing, it makes sense, but when splitting H files, how does that keep spatial locality? Are the splits by necessity both written to the same node?
So the splits happen in multiple phases. First, it's like a bit asynchronous. When you signal a split, you basically enter in the meta table that there is a split that is ongoing, so the region is being split, but you don't immediately split the H files because that would take too much time. You would have to stop the entire system saying, hey, wait until we have split the H files physically. That's bad because you make the system unavailable. So instead of immediately and synchronously splitting the H files, we just mark it as splits, but still use the old H files at first. It's less efficient because you need to scan the entire H file, even though you only want to read half of it. And then at some point, we will physically split you schedule basically a later actual physical split of the H file, right? But it can happen asynchronously and later. But the moment you do that, the moment you split the H file, you create new H files. And because you're creating a new H file, you're again creating new blocks and you again store them on the same machine. I have one more part of the answer to the question. Is it the same region or not? Well, it depends. Because at first, when you split a region, the two new regions, the two half regions stay on the same machine. So then if you split the H files, then it will create the new H files also with the first replica on the same machine. But it could also be that after the split, the region server has too many regions, and the H master decides to move one of the two halves to another region server, right? And so at that moment, you would have the new H files of the one half that are maybe the old region server, and then you write them locally to that machine, and the other half of the H files will be handled by a different machine, and then the first replica will be on this other different machine, right? But don't forget that since it's HDFS, all the machines can see all the data. It's only a matter of how fast, but they can all see all the data. So it's just reading HDFS and copying back. Does that make sense?
Yeah, he got it. Thank you.
Okay. You really have to have this in mind that in HDFS, you don't have random access, read or write. You just delete files and recreate new files. Maybe you append at the end, but that's all. You can only do that. So whenever you compact, whenever you split, you are creating fresh blocks, and these fresh blocks will have a copy on the same machine on which you are sitting. Who is with me? Right? Okay, awesome. So this is what we mean with locality, the fact that we can have local writes and reads as often as possible. Okay, so that's the nice picture with yes. Mm-hmm.
Okay, here all these tools are just tools built on top of HBase because HBase doesn't natively support SQL.
Mm-hmm.
So you need these tools to access HBase through SQL, right?
Mm-hmm.
Okay. Yeah.
Yes, absolutely. So to say a few more words, the reason why it's like this, like a puzzle, has to do with the scale. We are talking about thousands of machines. We are talking of something of a complexity that is way beyond something like PostgreSQL. That is the reason why instead of solving the entire problem with a single technology, which would be borderline impossible, instead, the engineers solved the problems one after the other. So they first solved the problem of storing two-dimensional grids in a primitive manner with get, put, delete, and scan. And then other engineers built other components on top of that bring back SQL. This idea of having this puzzle and the components where each component does one thing and then you connect the component together, that's something very natural for computer scientists, right? But this is really divide and conquer. You can have something much more robust and stronger if you design your systems in this way, rather than a single monolithic technology that does everything, right? And by the way, if we had tried to directly build an ACID compliance technology on top of a cluster of machines directly instead of the components, in 2025, it still wouldn't exist, and I wouldn't be teaching it to you because it's still ongoing, trying to bring ACID back. Now with the lake house and so on, it's very recent. We are getting there, but this shows the complexity of the task, that it's very, very complex. Right. Okay. All right. Oh, another question?
Yeah, when you say that compaction and flushing brings like locality, so while we are flushing a H file, so generally when we flush, it belongs to the same store, which of the region that we are writing the data to. So still, it's like when we are compacting different regions that belong to the same store. If when we are generally compacting. So if it belongs to the same store, the data nodes are already present on the same, the data is already present on the same data nodes. So even if we are compacting it, it's still, the data does not move. So how does it bring locality? Like when I imagine it, it's like still present on this same node.
Yes, so first one precision, an H file will only contain data from the same region. You will never have an H file that has data from multiple regions, right? Because there's really a strict compartmentation across regions. To answer your question, the reason why this might happen is that HDFS, I would almost say, is alive, right? The blocks are there, but at some point there might be a lot of blocks on the same machine, and the machine starts to be full, and there's not room anymore on that machine. And so you have utilities and tools around HDFS that allow you to periodically launch load balancing activities. It means that when you load balance, you notice, okay, there's too many blocks there and not enough blocks there, and then you have a daemon that basically moves the block to this other machine that has less. This is the reason why this might happen. If there were too many blocks on the machine in the middle, then maybe as part of the load balancing, some of the blocks were moved to other machines. Right? Does it make sense?
Yeah.
Right. But if there's no load balancing, then indeed there's no reason why the replicas would go somewhere else. Another reason, also to answer your question, is when a region is moved to another region server, then the replicas used to be on the old region server, but the new region server will no longer have a copy of the replica locally. Do you agree with that? Because it's another machine, right? And when you move to another machine, you don't move the blocks with it. You just reassign the responsibility. But when that new region server that took over the region will compact for the first time, it's going to have to read remotely the copy of the blocks from the old H files. But the new H files that are compacted, they will again have a replica on the same machine, right?
So, but like when we even split it, when we even split like a server, then also it might be the possibility that it's going on different nodes.
Yep.
So in that case, the splitting actually like brings down locality as well, because still the nodes which still the data points will remain on that machine.
Yes. You're right. It's basically a race condition between when do you start to physically split the H files and when the H master might decide to move the responsibility. If the H master doesn't immediately move the region to another region server, and you already have split physically the H files, and then later the H master moves the region, then you lose locality. But in the other direction, you're absolutely right. If the H master is very quick upon the region split to say, okay, now that region goes there, but you have not yet physically split the files, then you will have locality, because when you split the file, it will be split on the two machines, each on their own, right? And then you create locality again, right? So basically the loss of locality happens if moving the region to another region server happens after the physical split of the H files. Does it answer your question? Yeah, awesome. All right. Then I'm going to move on to actually answering the other question that was asked about how do we take it to multiple regions. but I'm going to do it after the break. So we are going to have a coffee, and I'll see you in 15 minutes for this.